Okay.
And then it touched her. Oh, sorry. I have a question. Why am I a mushroom? No. Yeah, I don't know why I said that word.
He can assist the way. Okay.
You know what that reminds me of? Just in case. Oh, one quick thing.
Yes.
Physical class when just said it to class, I think lots of people think, oh, just so cute because she was really short. But now you're like a grown woman. It's like, oh, just pretty. Wait, what is that in class? In physics, when you stood up there. Because I never actually looked at the video. Auntie, why are you checking me out?
Okay.
Oh, take it back to your mother.
What? Okay, I don't know. Okay, girls. Okay, so first thing we need to do when we're determining how to graph. So this chapter is all about finding relative maxes, minimums, right? Critical points. But first, when we're doing the graphing, usually they give you like a function, right? And you need to determine like where are the inflection points? Where are the relative maxes and minimums? So as we talked about before, when a graph is increasing, its slope is positive. When it's decreasing, the slope is negative, right? If you talk about its prime, if the prime is increasing or decreasing, that tells you something about its derivative, which is the second derivative, positive or negative. Then this also tells us something about the concavity. So we know it's concave up when the second derivative is positive, right? If it's a concave up graph, it has to be constantly increasing in slope from right to left, left to right. So like we said, when it's concave up, it's a negative slope and then 0 and then a positive slope. So we can see the slope is clearly increasing the whole time. So if you were to graph the prime, it should go up to the right. You don't know the shape, but you know it goes up to the right. If it's something that's concave down, it's going from positive slope to 0 to negative slope. So that means it's a decreasing. The slope is going to be a decreasing function. Okay, so those are the most basic things. Now, second thing, what else do we tell about the original function? If you have a slope of what? If you have, when you have a horizontal tangent, what does that tell you about the first derivative? Horizontal tangent becomes the slope is 0, so it becomes the x-intercept, right? What else do we know? What other points matter in the original graph and then this one? Does the x-intercept on the original graph tell us anything on the second derivative, the first derivative? X-intercept. No, x-intercept actually doesn't tell you anything because x-intercept tells you the point of inflection tells us something, right? Point of inflection tells us something. What does it tell us? Relative max and minimum. Okay, so if I know the original function is increasing, like concave up, so when concave up meets concave down, this is considered point of inflection, right? Or you could say if it's like concave like this, that's considered a point of inflection. Concave down, concave up. If it's like this, is this a point of inflection? Right, because they're both concave down, so that doesn't count. Okay, so when a concave up meets down, then that tells us that the second derivative will be right, plus minus. We get, actually, what do I want to show you? What does that tell us about the first derivative? So when the original is like this, the first derivative increasing and then decreasing. Is that right? Concavity tells us increasing, decreasing. So if the first derivative is concave up, then concave down, then you know it has to be increasing, then decreasing. Therefore, here must be the relative maximum. Right, that location. So that tells us we can figure out a relative max. And then if it's the other way, if the original function is a down meets up, like this one, down meets up, then this point has to be a relative minimum, because that would be heading down to heading up. This must be relative min. Right, so then we know this is either relative, max, or min, right, points of inflection. Okay, what other important things do we know about a graph? So those are the key ones. Those two are usually what we're looking at, horizontal tangents and points of inflection. The other ones, not as important. I think we can figure it out later, I think, for the first derivative types. Okay, so let's, how can you tell a relative max from an absolute maximum? What's the difference between a relative maximum and an absolute maximum? The y value. But, okay, let me graph something. You tell me. Okay, let's say it's like this. Let's say this location is the same spot, like there. Okay, this is position A, B, C, D, E, F. Okay, that way I don't have to label the coordinate. Okay, let's say that's those spots. Okay, which one is the relative maximum, and which ones are relative min? And relative minimums. Where are the locations? When x equals We have relative maximums located where? At x equals. Relative maximums at C, E, anything else? No, yeah. So C and E. Why isn't A included?
It's not the other side.
Right, it's not relative. It doesn't have neighbors. So usually you have to think about you are the tallest one, or like the highest y value next to you on either side. You have to have lower values. So this is considered a relative max. That's considered a relative max. But this one doesn't count because you only have values to the right but not to the left. So this is not considered a relative max. Okay, then what a relative minimum? So B, D, but not F, right? So B and D, whatever values those are. What about a absolute max? That means it's the greatest y value. It doesn't matter if it's not relative. It could be an endpoint. So an absolute max, in this case, the highest locations appear to be C and A. You see, I was trying to show that the same y value. Is it possible to have two relative maximum values, or two relative absolute maximum locations? Yes. If the two y values are the same, it's possible that you can have absolute maximums located at both A and C, right? They happen to have the same maximum y value, like y value, let's say. In this case, you could, okay? If I had A be a little higher, then A would be the absolute maximum. How about the absolute minimum? F, right? Does it have to be an endpoint? Does absolute min and max have to be endpoints? No, right? I could make this point very low. It could be like that, right? Then this location would be the absolute minimum, right? The lowest spot, right? And if I made this a bit higher, that could be the absolute max. If this one were the highest, that's the absolute maximum, right? Okay, like in this second scenario, A, B, C, D, E, F. Okay, in this case, Audrey, let's see, absolute maximum. C, relative maximum. C and E, relative minimums. B and D, right? Absolute minimum, D. Yeah, that's it. If A were an arrow. Okay, if A were an arrow, then you wouldn't be able to say. There would not be an absolute maximum doesn't exist, right? If it keeps going, is there an absolute max? Because it goes up to infinity, right? But if usually they cut it off. They'll ask you, what is the absolute minimum from something to something? They'll cut it off. So if they cut it off, like they cut off the endpoint, then you would be able to say which one. That's the absolute maximum value. That's why when we do our analysis later, we're going to have to find the relative maxes and then compare it to the endpoints. That's why we compare the endpoints. We check these 2 points, find out those y values. Then you check the 2 endpoints just in case to see if those happen to be bigger than C or E. Okay, so that's absolute max, absolute min. Now, which ones are considered critical points? How do you find critical points? What's 0 or D and E? It's a derivative. It has something to do with derivative. What is it? Critical points exist when f prime is either 0 or D and E. That means the slope is 0. Is that a horizontal tangent? Some sort of horizontal tangent. Yes. What's D and E scenario for the slope? What does the graph look like when the vertical tangent? So basically, you're looking like for a vertical tangent, or it could be just doesn't exist, like sharp turns, right? All of those things could count, right? So for example, this, could it be 0 scenarios? Give me some possibilities. It could look like horizontal tangent, like this. That could be, right? It could be this way. What's another possibility? Maxes, mins, right? Those are all these, right? What other ones can you think of? When the prime is 0. That's about it, I think, right? That type of graph. You have these types. Okay, then how about D and E? So this is the, okay, so it is prime D and E. What's a possibility? It could be like this. Is that right? Vertical tangent? Right? It could be this way. Could be like this. Very steep like this. Right? Something like that. So these all are count. Or it could just be a sharp turn. I could just have this. Is this C and E also?
Serena!
Right? And then like this?
Say hi. Do you want to say hi?
She's coming this way. I think she's coming into this.
Serena! Is she coming in their class?
Yeah.
Serena!
Well,
Hey!
okay, hello. Okay.
You have to go class now?
Oh, hey, this is Lou.
Okay.
This is Lou.
so the grades, the results. Okay, all right. Let's continue.
Actually putting it up next week?
No,
I don't want to know now.
it was that bad.
No, I probably got an Wait, but I probably got better than my last test, so I think I want to. I don't know.
Okay, all right. So then these are all possibilities for D&E, right? We have sharp turns. We can have just like something like this, right? These are all, if it's continuous. Obviously, jump discontinuities would be considered.
So those ones are for 0, right?
Right, these are all for 0, critical points for 0. These are critical points for D&E. Okay, that could be what the graph looks like. Okay, now what about a stationary points? What are stationary points? Anyone remember? Stationary point is when the prime is 0. Yeah, so it's a special kind of critical point, yes. So when the stationary points are just these like types of scenarios, right? It could be like just like these. So basically critical points include this one and this one, but stationary points would be just when the derivative is 0, just when the slope is 0. That's it. It's just a naming convention. So they ask you identify all critical points. Then you'd have to identify the critical. What would be the critical points on this graph? This is a pretty easy graph, though. What are the critical points? Just all of these horizontal tangents. So B, C, D, and E. And then we don't have any D and E's on this graph. I didn't show any slope D and E. F and A doesn't count, right? Yeah, because they're the end points. And then all the slope also at this location is not D and E. I didn't make it really, right? I didn't make it vertical, right? So then how about stationary points? So they all count as stationary points, too. Yes, because they happen to be horizontal tangents. D and E. For the derivative, this one, I don't think you count this as a critical point. No. A is not considered a critical point. I think you're only to count the ones.
The only one there's like both sides.
Which one?
Like B, there's 2 sides to it.
B is 2 sides. Yeah.
So only one 2 sides.
Mm-hmm. Mm-hmm.
And
Yeah, A and F. I don't think we count A and F as critical points because the slope. Okay, because there's no slope from one side. It's only a one-sided slope. Let me check on that. I don't think A and F are considered critical points. I'll check your textbook. Does anyone have their textbook? I don't think you count the endpoints. Endpoints I don't think are counted as critical. I think it's just going to be if your slope is actually D and E. Like when a slope exists. I don't know. Actually, when the tangent exists, I think you have to be able to draw the tangent also. But you can check. I'm going to do a problem and I'll check your book, okay? So how do I do this? If I'm trying to do y equals to 1 over 1 plus x squared. Okay, let's first do it using the pre-calculus method, and then we'll come back and use the calculus method. So this type of question, when we did it in pre-calculus, what do? We looked for the vertical asymptotes. Are there any? If the denominator is never 0. No, there's none. Okay, then we look at horizontal asymptotes. What is it if the top degree is less than the bottom? The limit goes to 0, right? When you take this limit to infinity, we know it's going to be 0. So this will be y equals 0. It's a horizontal asymptote. And then when we graph, we think about, are there any x-intercepts? None, right? Because the numerator is never 0, so no x-intercepts. Then we think about the number line and what we can show on the number line. Usually on this number line, we want to think about any x-intercepts and also any vertical asymptotes. So anything that makes a numerator 0, anything that makes a denominator 0. So actually, there's nothing here, right? There's no x-intercept and there's no vertical asymptote. So in this case, what's our leading coefficient? When you look at the leading coefficient, you can see the top is 1, a 0, positive. The bottom is positive. That means this whole number line is positive. No matter what number you substitute here, any real number makes this whole expression positive. So it's all above the y-axis is what it means. So when we graph it, what does it look like? You have vertical asymptote, none, right? We have a horizontal asymptote of 0. That means it's going to approach 0. It's going to be something that looks like a bell. We have a y-intercept, though. Set the x value to be 0. It's 1. So it means it goes to 0 and 1, and it's going to approach the horizontal asymptote on both sides when it goes to infinity and negative infinity. So this is what we know from pre-calculus. This is a rough sketch, right? Like that little hill. Okay, so that's it. But now from a calculus perspective, you need to figure out what are these points of inflection. When does the concavity change, right? So if you, like this point and this point, you see it's concave down here and it's being met by a concave up. So this location, you need to figure out those x values, right? We need to find out the points of inflection. So let's now use derivatives, right? We have to do first derivative, second derivative to find that. So if you're saying So from a calculus perspective, first let's take a, you don't want to use, do we want to use quotient rule for this? Definitely not, because what, the numerator is just like a constant number. So we prefer to rewrite this and use chain rule or power rule on it, right? So just write it like this and take the derivative. So bring down the power, subtract by 1, and then do the derivative of the inside, which is 2x. Now let's take the second derivative as well, right? So rewrite this with no negative exponent. It's a little easier to look at. Negative 2x over 1 plus x squared to the second. Okay, that's my first derivative. Okay, I'm going to graph something about this, and then let's take the second derivative. Okay, so first, let's take this, and let's see what key ideas we can pick up from here. So the first derivative, I'm going to do the number line for the first derivative. What do I want to show on the number line? I want to show the x-intercepts, and then we can do also any vertical asymptotes. So the x-intercept's obviously 0, right? On the bottom, what makes this 0? Nothing. 1 plus x squared is never 0. So we only have a 0 here to show. Can this equal 0? Sure, right? The numerator, the prime could be 0. It could be equal to, so I'm going to make this solid. The leading coefficient is what? Positive or negative? Top is negative, denominator positive, so negative over positive, negative. This only works when it's what? This type of thing is only when it's, if it says ln, sine, e, then you can't use the signs, right? You can't use the plus minus concept. But if it's just polynomials, you could use the, right, the switching of signs, of course. So here I have all of this doesn't matter. Second degree, we don't have a 0 to go across. But this will be negative and then what? Positive. Right, if you're not sure, you can always substitute a point. So that's it. So then I know that we're going to alternate here. So then f is then going to look like what? Increasing, then decreasing. Right, because the prime is positive or negative. Remember this? Okay, so keep this in mind when you're doing these. So increasing, decreasing tells you something about the derivatives. Right, those are the key ideas. So we know the primes are plus minus, which tells you the original graph is increasing or decreasing. So right now I have a relative maximum at 0. Right, that's the first thing I figured out. So from the first derivative, I figured out the relative max. Okay, now let's take the second derivative. So one more time, f's second derivative. This guy, so we're trying to do, what do you want to do this time? We got to do quotient rule probably, right? You could do product again, but quotient's fine too, either way. So square the denominator, 1 plus x squared to the 4th, denominator squared. Low, keep the bottom. D high, derivative of the top, minus high, top, derivative of the bottom. So it's 2, 1 plus x squared, subtract the power by 1, do the inside, which is 2x. Okay, now you have to factor if possible, right? So simplify. So here I see I have this, 1 plus x squared. I have a 1 plus x squared there. Might as well take one of them out. I can also take out this negative 2 here, right? That could be taken out, this one, and I guess this one of the negative 2's. Okay, so I can take out negative 2, 1 plus x squared. Yeah.
1 plus x squared to the 4th.
I square the bottom. Low squared. Low, low. Or square the denominator. We're doing quotient rule. So then I took this out. I took out one of them and the negative 2. So I have one of these left. 1 plus x squared. That's gone. Negative 2. This is gone. So I'm going to have negative x. Let me think about this. Okay, let's take this one out. So that's gone. So it's negative 2x times 2x. So it's 4, negative 4x squared. And then this is gone, right? These two. So it should be negative 4x squared. That's right. Okay, on the bottom, same. Okay, so that's a negative 3x squared if I combine. I don't think I can simplify anymore. So that's it. Negative 2 times the 1 plus x squared, 1 minus 3x squared, over 1 plus x squared to the 4th. Okay, then from here, let's graph that. What's the second derivative? Okay, second derivative show x-intercepts or any vertical asymptotes. I have no vertical asymptotes, none here. On the top, that's nothing. This one is positive negative what? That's 3x squared equals 1. So positive negative square root 1/3, right? It's like this. So I'm going to show both positive root 1 over 3 and negative root 1 over 3. And then that's the numerator, so it can be equals to. My leading coefficient is, look up here, this is positive on the bottom. On the top, the leading coefficient, the biggest degree, you can see is what? This is a negative number times a positive times a negative. So overall, it's positive, right? Are there any double roots or even roots here? There are no even roots. Sometimes people confuse a square for an even root. That's not an even root. It's one root that's positive square root 1/3 and the other one's negative square root 1/3. If you have something like like this, that's considered a double root. So if it were like 1, as you guys know, then it would be plus plus, right? You don't alternate across that one. It wouldn't change signs. But in this case, right, there are no double roots here. So it's going to be alternating. So it'll start positive, negative, positive. Okay, then the next one, f, what does that tell us about f? So if our second derivative is plus minus plus, then that tells you something about the concavity of the original function. That means the concavity of the original function is concave up, and then down, and then up. So if it's concave up and then down, what is that called? What is this point then? It's point of inflection, right? So this is point of inflection. That's inflection point. So both of them are going to be inflection point and inflection point. Yep. Those are the two key ideas there. Okay, so then using that, let's graph. So then you have to find the points, sub it back in, and do it. So if you sub the points in, let's find them. So my inflection points are positive root 1/3, negative root 1/3, sub back to the original function. I know it's a pain. You got to square this. It's going to be 1 plus 1/3 to the negative 1, and the other one is 1 plus, and it's also squaring the same thing, right? 1/3. So it's going to be symmetric to the y-axis here, the negative 1. Because this is going to be 4/3, so reciprocal 3/4. 3/4. Okay, so 3/4 for both of those. My relative maximum I have there is 0 at 0. So sub in 0, obviously at 0, 1. And then we're going to sketch it from there, right? Just like we did before. So we kind of had an idea from earlier from pre-calculus. We knew what the graph looked like. So all we need to do is put the specific points in. Okay, so I have 0, 1. The other one, okay, this root 1 over root 3 is approximately, let's see, 1.3 something. What's the value? Can someone calculate it? What is it? Otherwise, we can't sketch this. What is this going to be? Square root of 1/3 and then negative that. What is that? 0.57. Okay. Okay, and obviously this is negative 0.577. Okay, so obviously on this test, is she allowing any scientific calculators? Okay, so that means that you, so for the, yeah, maybe the numbers will be nice. The numbers will be nice, or you're going to estimate. Right? You might just estimate. So then root 1/3, you'd say, okay, that's like 0.3. So the square root of that is definitely less than 1. You'll just graph something and just label. You won't have to graph it to scale, if that's the case. Okay, so you'll just say, okay, that's about, so you wouldn't be able to know on this side what it is, but 0.57734 is like here. 0.57734, something like that. Right? And then you know it's like this. Concave down, this part, and then the next one concave up, and this is concave up. That's it. Okay, and then you know it doesn't cross through this horizontal asymptote because you had an idea of what it looked like before. And then the locations, for this one, you get a label. So it's going to be negative root 1 over 3, 3/4. This will be positive root 1 over 3, and 3/4. Right, so what would you say is your relative maximum? This location. Yeah, 0. Actually, does she want you to give the maximum value or the locations of the relative maximum? Both. So she'll say, oh, find the location. You have to say, at x equals 0, there's a relative maximum of 1.
No, you say there's a maximum of 1 at x equals 0.
Okay, then say it that way. Okay, there's a maximum of 1 at x equals 0. How about relative minimums? Are there any? No, why not? Because you get infinitely close to 0, but you never touch 0, so you can't find that location. So yeah, there is no relative minimum. Absolute maximum, also the same spot, right? And then critical points. Critical points. Horizontal tangents count. Horizontal tangents, so this is a critical point. X equals 0 is a critical point. Any other critical points? This derivative is 0 or GNE. So there are no other locations, right? Because this is not quite 0 here. It's going to approach 0 but never hit 0. So this is the only one. Stationary points, that's also a stationary point because the derivative is 0. So it's both a critical point and a stationary point, right? Okay, so that's it. Okay, so let's try one. Yes?
What was the point of doing f prime and the graph is 0?
F prime and F double prime? This one. No, this part. This to find relative max. Yeah. So when you do the prime, you find the plus minus. That'll help you figure out if it's a relative maximum or minimum. And then when you do the second derivative, you're going to find the inflection points. That's it. Every time you do it, it's the same process. Okay. Let's do one with e's and L or e in it. Okay. So if it's like e equals 2, if it's y equals 2, x times e of x. It's like homework. Homework questions have stuff like this, right? X times ln e of x. All right, how are we going to do this? Take the first derivative. So product rule. Do the first one, so it's 1. Keep the second one, plus keep, and then do. Okay, factor. Take out the e to the x. It's 1 plus x, or x plus 1. Okay, next do the second derivative. I'm just going to do them together and then discuss them after. Okay, second derivative one more time, product rule. So do the first one, e to the x. Keep the second one, plus keep, and then do. That's 1. Okay, then I can take out e to the x again. I can see that's x plus 1, and then don't forget there is a 1 here. So it'll be x plus 1 plus 1, so it's x plus 2. Okay, then go ahead and show the first derivative number line, and then do the same thing for the second derivative. How do you guys do it in class? You just do the number lines too, and then just plot points. Same thing? Okay, so first derivative, I have, what makes this 0? Never, right? Why? Because e to the x is a graph like this. It's always greater than 0, isn't it? It's an increasing function. The base is 2.7 something. But e to the x is always that. So it never touches 0. So only this one needs to be shown, -1. It can equal -1, right? The leading coefficient is positive, so I know it's going to be plus and then minus, yeah, for this one, because this part is like a polynomial, right? So we know it's plus minus. Okay, so then you say the original function then would be decreasing, then increasing, so this is a minimum. Then do the second derivative. So f, second derivative. Again, that can't equal to 0, but this one can, -2. Leading is positive, so plus minus. Then I know it's concave down, then concave up. Right? That's how you concavity. If the second derivative is negative, it's concave down. Second derivative positive, concave up. So that must be an inflection point. Okay, so if I have that information, let's see if we can graph it. What do we know about this? Any x-intercepts, any y-intercepts? Yeah, that you can easily see. So right, a y-intercept setting x be 0, so I know it's 0. And then of course at 0, then it means x-intercept must be 0 also. Okay, so then I can show. Okay. So it definitely crosses here. That's the only point we know. And then the minimum occurs at -1. Somewhere along here it's a -1. And then we have an inflection point at -2. And what does this look like? It's going to minimize here, and so it's going to head down and then head up, right? And then inflection is concave down, then concave up. Okay, does anyone have an idea of what this looks like already? You already know it kind of looks like that. Except doesn't cross this one. It doesn't cross this one. How come? Because when you start subbing, yeah, it only crosses at 0, 0. It doesn't cross again. So it means this is going to be like a horizontal asymptote. So we're going to only cross once. So it's going to go from positive and then down, hit this one to be minimum, and then come back. So it's going to go like this. And then actually you could sub the points too, and you'll figure it out also. You have, oh, this is the inflection point. This is the inflection point. So I have, it's all going to be concave down, up, until this location, and then it becomes a concave down. Okay, you could sub the point. So we have this location, the minimum. I didn't graph that right. Lowest spot. Okay, this lowest spot, -1, sub it in. So it's -1, sub in -1. That's negative e to the -1. Right, so that's that location. And then the other one over here, this one is -2. Does she want you to label every single point? Yes, okay, so -2, you got to sub in to there, so it'd be -2 e to the -2, which is over e squared. Yeah, that's it, okay? And then if you sub on this side, it just gets bigger and bigger, as you can see. If you sub positive numbers, it goes to infinity. So it heads like this, minimum, comes back, and then you can see as you sub smaller numbers in, you have an idea of what it's going to look like. Almost 0, right? It's like -100 e to the e to the 100. So this is a very big number. A small number over a really big number is about 0, but not quite 0. So that's why it's going to keep approaching it, right? So that's it. That's the idea. Any questions about that? Inflection? No? That's it. Okay, so then next, so then the relative minimum is at -1. The relative minimum value is -e to the -1 at -1. And then it's also your critical point, right? And it's also a stationary point. Anything else? Relative max? None, right? How about other things? No, right? These things you can't say anything about them. Stationary points are when the prime is 0. That's just the definition of a stationary point. So that's considered a stationary point. And a critical point, both things. Okay, let's see. If I have f of x equals to 1 plus x to the 1/3 times x. Let's try to graph this one. This is a really complicated one. Okay, so first derivative. Okay, do the first one, bring down the power. Subtract this by 1. Do the insides 1. Keep the second one, plus keep the first one. Do the second one. Okay, so I need to take out what? Now with these exponents, I should take out the negative 2/3 power. You take out the smallest power you can, then most the negative one you want to take out. So if you want to take out 1 plus x to negative 2/3, now you have to think I'm multiplying everything by this thing to the positive 2/3. So add positive 2/3 to this. That means this goes away, right? So you're going to be left with 1/3 of x, and then you could actually take out the 1/3 too if you don't want the fraction. Let's take out the 1/3. That means we're going to multiply this by 3. So anyway, this all goes away. So x is left plus. So you have to think I'm adding 2/3 to that, right? Because I took out an x whatever to the negative 2/3. I'm plus 2/3. So that becomes 1, doesn't it? So it becomes 1 plus x to the first. So it's just 1 plus x. And then what else? If I took out a 1/3, that means I'm multiplying this by 3. So it's like 3 times of 1 plus x. Isn't that what it means? Okay, then multiply it. So you have 1/3, 1 plus x, and negative 2/3. And this is x plus 3x, which is 4x plus 3. Okay, so that's the first derivative. Okay, second derivative. So do it again. So bring down the power. So negative 2/9, 1 plus x, to negative, subtract 1, so 5/3. The inside is just 1. Keep, plus keep this one, and then do this one. Okay, what should I take out this time? So now I can take out a 1 plus x to the negative 5/3. I want to take out the more negative part. And then what fraction should I take out? 4/3. Yeah, if I take out 4/3, then I'm going to multiply by 3/4. Yeah, I can make it a whole number. So, wait, hold on a sec. If I took out 4/3, then I'm actually multiplying by 3/4. It's still fractions. I don't want that. I want to take out the bigger number, the 9 on the bottom. So if I take out that, I can multiply this by 9/2. Let's see. Yeah, then it becomes a whole number. Okay, so I'm going to take out this one, 2/9. And the 1 plus x to the negative 5/3. Okay, so then when I do that, there's a negative there and this left, so it's going to be a negative 4x minus 3. Second part, this one I got to add 5/3 to it. If I removed a negative 5/3 power, I got to add that, so that becomes 1. So this whole thing stays. And I also removed 2/9, so I got to divide it by 2/9. So it's going to be this 4/3 part times reciprocal of that. Sorry. So it's going to be 6. So 6 times of 1 plus x. Did I take a negative out? I did not. Hold on a sec. I didn't. Yeah, it's okay. It's okay. That first one stayed negative. The second one's positive. Okay, like this. All right, and then simplify. So I end up with 6 plus 6x. Okay, so it's a 2/9 times 1 plus x to the negative 5/3. Add those, which is 2x. Add those, 3. Yeah, that's right. Okay, so then up to here, okay. Next part. This is second derivative. Okay, now let's go ahead and show the number line. So the hardest part about this is keeping everything straight once you factor. Okay, then the next part is okay. So f first derivative. I can see I have a negative 1 here. The other one, I've got negative 3/4. You see that? Negative 3/4 and negative 1. Okay, now can this number in here, well, there's a square here, it's considered an even power, right? Even though it's 2/3, meaning I am doing like squaring and then cube rooting, right? And then over 1, that's the meaning of the negative, right? You square and then cube root. So is this ever going to be negative? Yeah, even if I sub negative numbers in there, it'll become positive, so you're okay. So anyway, when you see the even power here, don't change signs for that negative 1. So I need to keep that one positive, or keep it the same sign across these two. So then leading coefficient is positive. You see that? X, 4x, both those positives, starting positive, positive, negative, and it usually goes plus, but it doesn't this time because the negative 1 is that square, right? That's even power. Okay, so then if it's plus, minus, minus, all right, then what do I know about f? Down, down, up. So that means this one is not a relative max or min. So this is like one of the scenarios. You might say, oh, every time I do this, the zeros end up being the relative maxes or min. This time it's not. Only this is. So this is a relative minimum. Here, that's not. Right? It could be something like that. It could be this is just another horizontal tangent, right? F prime is 0, but it's not a minimum or a maximum. That's possible. Okay. So the next thing in here for the second derivative. So f second derivative. So this one, -1 and -3/2. That's not an even power, so sign will change. This is odd, so sign is going to change also. Leading coefficient, positive, so plus, and then minus, and then plus. And then I have first, that means the original graph is going to be concave up, down, and then up. That means both of these are considered inflection points, right? Both inflection points. So I have inflection point here and an inflection point here. Okay, so sub and in, see what we have. So I have, what do I have? X, okay, so I have x-intercepts, y-intercepts. So x-intercepts, y-intercepts when x equals 0, I can see that's 0. Y-intercept 0. X-intercepts, are there more than, so y-intercept 0, are there 2 x-intercepts? What two things make this 0? So both -1 makes this 0, right? And 0, so I have 2. So I have x-intercepts located at -1 and 0, 2 locations. Go ahead and substitute the minimum value, the relative min is located at -3/4. So, yes? No, we're still doing the same problem. Still doing this question here. So the relative minimum, sub it in there, and it's a messy number, so it's like 1 plus -3/4, so it'll be 1/4 to the 1/3 times -3/4. And the other one, let's see. Okay, I don't have a max. I have inflection points. My inflection points are at -3/2 and -1. So -3/2, sub it in, you get -1/2 to the 1/3 times -3/2. So I assume if you're not going to have a calculator, the numbers will be nicer. Okay, so the next one, if you sub -1, you have 0, right? -1, yeah, 0. Okay, so let's try to graph it. Attempt to graph. Okay, so I have no space here. I'm going to erase this one. Okay, so I have an x-intercept at -1 and 0, y-intercept at 0, relative minimum and maximum, so it's at -3/4. I'm going to make this a bit bigger. Okay, -3/4 around here. This number here is something, -3/4 something. So I'm just going to graph something here. So it's a small number. It's less than 1. It's 1/4 cube rooted, right? And then multiplied by -3/4. So whatever it is, it's less than -1. I mean, greater than, it's not going to be lower than 1. So it's somewhere here. You could just label it if you don't have a calculator. Then the next one, let's see, that's my lowest point. Inflection point at -1, 0. So this is an inflection point. I'm going to put an X there to remind myself to change concavity. And this one is also -1.5. Somewhere over here, -1.5 in this location. So you'd have to sub the points. You're just not going to be able to get it. So you have this as, this location ends up being 1.191. The other one, that's negative 1.5, positive 1.191. This one, minimum, is a negative 1. What is that? Negative 1. I didn't sub this one. Negative 3/4. Negative, so this is 0.472, right? And then that other location there is, this is 1.1 something. Okay, I'm not going to be able to draw it to scale. Okay, so this is going to be somewhere over here, negative 1.5. So negative 1.5, positive 1.191. Okay. And then you could see this one. Okay, so it should be concave up and then concave down. Let's see. And then concave up. So it's similar to the last one. You have concave up meets with the concave down between here and negative 3/2 and negative 1. So this is concave down. And then the last part is concave up. And then you check to see that you had a relative minimum at negative 3/4, which we did. We don't have a relative minimum at negative 1. Yeah, that's right. And there's nothing here except an inflection point. That's it. Any problems? No. Good? Okay. So this type, I think you guys know how to do. Let's see. How about inflection points, all those other things? Let's talk about that. Relative minimums, relative maximums. And then like critical points, stationary points. Okay, first one, relative minimum is located at only here, right? Any other ones? No. So relative minimum, you'd say you have a relative minimum value of, you said you have to mention this one first. Relative minimum of negative 0.472 at x equals negative 3/4, like that. That's how she wants you to mention them? Okay. Or you'd say like the relative minimum is located at x equals negative 3/4. That should be okay also. It depends on whether or not you need to mention the value. Okay, relative maximum, none, right? Because they kind of go up to infinity. So, and then unless it cuts off, if it says like, oh, you want to take the domain between 1 and negative 2. If it's between 1 and negative 2, then you have to check out what the point at 1 is, right? Sub 1 in, and then sub negative 2 in and see which one's larger. Okay, so then in this case, no. Absolute minimum, same thing, right? And then absolute maximum, none. Critical points, what are the critical points? Negative 3/4, yep. Negative 1.5, both of those are horizontal. Are those both prime equals 0? We graphed that already. The prime is 0 at negative 1 and negative 3/4. So you say at x equals negative 1 and at x equals negative 3/4. Located at these two x values. Okay. Any stationary points? So yeah, both of them are stationary. Are there any D and E locations? I don't think so, except, let's see. We took, yeah, because there's nothing that was D and E on our graph for the prime, right? When we did the f prime, nothing was D and E. So yeah, so we have stationary, both same things. Okay. Yes. Negative 1.5. Negative 1.5 is, oh, wait, this is wrong. This is not right. This is supposed to be, I wrote wrong. I think I wrote a critical point, hold on.
Critical point is negative 1 and negative 3/4, and then the point of inflection was negative.
This is, yeah, negative 1, negative 3/4, that's right. Both of these were the prime was 0. This one and this one were both, wait, what did I graph? Negative 3/4 and negative 1. Oh, you know what? That's not, okay, hold on.
No, it is though.
Let me see what I graphed here.
It also happens to be a point of inflection.
Negative 1 is supposed to be, oh, wait, there's a problem here. Okay, hold on a sec. No, that's not a 0. In the graph, it doesn't look like a 0. You see how the slope is not 0? Okay, hold on. When we graphed this earlier, I erased the prime already. The first derivative was Let me write it out again, okay? So the first derivative was, what is it? Negative 1. It's not, yes, it's a d&e there, yeah. There's a problem there. Okay, so this is negative 2/3. There's a negative 4x plus 3. I put a solid here, I think, on accident. Because this is not solid, it's a hollow. Can you change that? Why is a hollow? Because it's negative. So it's on denominator. So you can't have, it's 1 over 1 plus x to the 2/3, right? X actually can't be negative 1. It's a vertical tangent here. So put a hollow there. This is a solid. And then the leading coefficient was positive, so or negative. So it would be negative, right? Negative, right? Negative, positive, positive. What we showed earlier? No, we did positive, negative, negative. Hold on. Did I graph this incorrectly? Hold on. F. I did this negative something, blah, blah, blah. Okay, so then the leading coefficient here is negative, or is it positive? It's just 1/3. Was that what I wrote earlier? Okay. There was a 1/3, not a negative 1/3, right? I don't know. I wrote something down here. Positive 1/3. Should be positive. So leading positive. Okay, so it should be plus, minus, minus. Okay, so as we wrote earlier, plus, minus, minus. So it was like down, down, up. Okay, so that is a min, but that's not. This is a vertical tangent, which it is here, right? So that's actually a critical point then, and it's not a stationary point. So critical point at -1 and -3/4, because this is our d&e slope, and this is the 0 slope. And then where stationary, you don't mention -1. Stationary only could be the locations that have slopes that are 0. So the only one with slope 0 is -3/4, right? That makes sense? Yeah. So then that's this one only. And then, let's see. Yeah. Then in that case, my second derivative, you should hollow out that -1. This one should be like hollowed. That doesn't exist, right? The second derivative, so the first derivative doesn't exist at -1. The second derivative won't exist at -1 either. Okay, so then this one, this is okay. This is an inflection point. That's allowed. Yeah, that's it. Yeah, so inflection point here, but actually that wouldn't be, it's still considered an inflection point. Which one? This one? Up, down, up. This is a point of inflection. Yeah.
But then you said how at the beginning you drew like a diagram that said when it's concave up and then concave down, so it looks like a tangent almost. That point in the middle is a critical point.
Concave up and then concave. This is a critical point. Yeah.
Exactly.
-1.5 is a critical point. Not a critical point. That concave up, concave down, that's an inflection point. That doesn't necessarily have a prime of 0. Okay, inflection points, this -3/2, right? Because you're changing concavity. And then this one. Yes, it can, if it's actually a horizontal tangent there. If this were a horizontal tangent and you have a change in concavity, it could be both an inflection point and stationary. But it's not a stationary point because when we did the prime, it doesn't show up as a 0. Yeah, that's how you know. So this one, it could be like, I just graphed it like this. This is a sketch. You don't know what it really looks like there. The slope there, it could be just something. You don't know what the slope is. We'd have to actually solve it, or sub it in. You'd have to sub the -1.5 into this equation, and you get some negative number. It's not going to be 0, though. Right? Does that make sense? Yeah. Okay, so then that's it. Okay, so then inflection point, you have all of them. Good. All right, so let's see. Any other primes? Let me see. I'm going to skip the ones that you can handle. I want to do ones that you might think are harder. Okay, so how do you, okay, first derivative test, second derivative test, both those things. Do you know how to test for relative maximum, first derivative? Have you been talking about that first derivative test? Yes. What is the first derivative test? It's when you find this. Yes, it's finding the maximum or minimum, but based on what? First derivative test is based on obviously doing one derivative. Second derivative test, you do two derivatives, and you check for whether it's greater than 0 or less. So let's write it out. So first derivative test. So you say, first I check for, this is to determine, both of these is, you're trying to determine the relative max or min. right? You use two different methods. If you use the first derivative test, first you check it has to be continuous. So f is continuous. And then you check that the prime at a certain value is 0. Okay, so first derivative is 0 there. And then it changes from a positive to a negative or negative to a positive. So like this. If you have the 0 here, right, and it goes from plus to minus, that means the original function is heading up and then heading down. That means this is a max. But if it starts negative and then changes to a positive at a, that means my original function is heading down and then going up, so then it's a minimum. See that? So this is a min, this is the max situation. So those are the two. So I think in words, I think the book talks about it as f prime at a is 0. And, okay, so if f prime changes from a positive to a negative about a, or actually from left to right, let's see, how's it phrased? F prime changes signs as you move from left to right. Okay, changes from positive to negative as, how's it phrased in the book? As you move to the right.
If it's from positive to negative, it could be negative to positive too.
I want to say maximum. I wanted to say, like, when it does this, it's a relative maximum. I don't know how the book states it. I think it'd be like f prime is 0, and f prime changes from positive to negative about, I don't know if you have to say about x equals a, as assuming from left to right. Anyway, f prime changes from positive to negative from left to right, I should say. Okay, so f prime at a is 0, and f prime changes from positive to negative from left to right. And then this means that you have a relative maximum. So fx equals an a, there's a relative max at x equals a, something like this. I don't know how your teacher stated it. Just follow whatever she wants you to write. Okay, the second one, f prime goes from the other one. So this one would be like f prime, so it's continuous. You have to say it's continuous. F prime at a is 0, and restate, right? F prime changes from negative to positive, from left to right. So then there's a relative minimum, I'll say therefore. Therefore, there's a relative minimum at x equals a, something like this. So that's the first derivative test. Okay, what's the second derivative test? That means when you test, yes, concavity. So when you do the second derivative and it's greater than 0, what does this mean? Yeah. How do we find a relative maximum or minimum? So if you say, what is a second derivative test? When f double prime is greater than 0, what happens? Which means you have a relative minimum, yeah, at that location. So that would be, you have to say that it's, if you get f second derivative, so if f first derivative is, let's see, yeah. So if you have f first derivative 0, and then f second derivative is less than 0, then this scenario is a concave down, right? Second derivative less than this way. So that means this one becomes our relative maximum, right? So then we have a relative max at x equals a, something like that. And then the other one, if f first derivative is 0, so it's definitely horizontal tangent, and f second derivative is greater than 0, then it's this way, right? Then a relative minimum is located at x equals a. That's it. That's the second derivative test. What else? What if it's D and E? Is there any scenario for D and E when the let me think. When it's D and E, could we have a relative maximum or minimum? It's possible. So we could have this scenario, right? That could be a relative max, but the slope could be D and E. It's possible to be. It's possible to be. I don't know if it's considered under the first derivative test. I think you could still test it under first derivative. So it would be if it's continuous and the slope is 0. It's these two scenarios. But if it's it is continuous. It's still continuous. Continuous function just means that you don't have to lift up your pen. It's not differentiable. It is still continuous. Yeah, it's not like this is a jump, right? So continuous means you can just like trace the figure, right? So it is still continuous, but the slope could be d/e, and then we could actually have relative maximum and minimums. It's possible. So another scenario, I guess, for this one, first derivative test, you could do this. You could say if f is continuous, and you have f prime at a is d/e, right? Doesn't exist. Okay, if that happens, doesn't exist, then it goes from, it could still count. So if it's d/e, then you could still do the same thing. If it goes from positive to negative, it's a relative max. Negative to positive, relative minimum, that counts. So we could say it changes from, goes from negative, let's say, to positive. That's relative minimum, right? Relative minimum at x equals a. And the other one, if the first derivative changes from positive to negative about a, then you have a relative max at x equals a, right? So that would be like this. If I have d/e, it could be, it's continuous is the main idea. Negative to positive, that's this one. Positive to negative, like this. I could have a vertical tangent here, and it's going from positive slope to negative slope. So it is a relative max at a, right, at x equals a. And this one, the other way, could be like this. So it could be, like that's a possibility. You could have d/e for slope, heading down, then heading up. So then that means you have a relative minimum at a, right? Yes, so those all count. Okay, so those are methods for you guys to look for relative minimums or maximum values. Okay, so what about this? What if you were looking at something like this? Let's see. Okay, so if this is supposed to be my prime, then what can I tell about the original function? Right, prime to original function. Okay, so I know it's always harder to go the other way. So it's like plus minus. Okay, so if we have first one, what does this say? So I have no prime at 0. d/e, right? Okay, so then what about the other things we can tell here? So we're looking at these two things about the first derivative. So the first derivative, I can see that it's above, it's positive here, which means it's increasing in this section. It's below the x-axis, so it's going to be decreasing in that section. And then what else can we tell? The first derivative, it's increasing, so it means concave up, and this one is also increasing, so it's concave up. So it's concave up the whole time, right? So what was that graph going to look like? There's also something here. Vertical tangent here, right? There's also something there. So, okay, let's do this. For this, we're trying to graph the f. We're going to go, right, I gave you the f prime, graph the f. Okay, so right now I can say it's a positive, it's an increasing, because of the plus, right? Above the x-axis, it should be an increasing graph and concave up, right? So it should be increasing concave up. This kind of graph. What's an increasing concave up graph? Which half of that? It's the right half. Yeah, so it's definitely going to go like this. Okay, so then the next part over here, this is a below, so it's decreasing below the x-axis. Decreasing. Below the x-axis, so it should be decreasing, and then it's heading up, so it's concave up. So decreasing concave up, that means it's the left side of this. It should be something that's curved like this and something that's curved like that. Right? So when you're sketching it, and then the slope we know is d/e. So that means that there's still a vertical asymptote here, or some sort of d/e slope, right, when they meet. So it should be like this, and then like this, probably, right? So maybe like this, right? And then you can check, is that right? My slope was 0, so it's close to 0, and it gets more and more positive until it goes to infinity. Right? Infinity up there. And then on the other side of that, over here, what is the slope? Negative infinity. And then it goes closer and closer to 0. So negative infinity, and then less negative, less negative, less negative as it approaches 0. So it's something like this. Right? The original graph. Like, you don't know how high, how low. It's just a sketch. The f prime is below the x-axis, so it's a negative value, right? So that means that the original function should be heading down, exactly. So if you look at this and you think about slope, this slope's positive. That's why they're all up here above the x-axis. The slope on this side is negative. So when you sketch it, it should all be below the x-axis, right? So that makes sense why it's down here. Because it's increasing, yes. Because it's heading up, because the value is on its way up, then you know it's a concave up kind of graph. But so you think, okay, what type of concave up graph is increasing? It's got to be like the right side of the parabola, something like this. So it should be a curve like that and then a curve back down like this, okay? That's it. So then the next one, what do we see over here? This one. So we know for sure it's going to be another vertical tangent, right, at 0, some sort of vertical tangent. And I know it's a, what, positive, so it's increasing, concave up. And over here, it's a also increasing, yes, because it's positive, increasing and concave down. Yeah, so increasing concave up is this part. Increasing concave down is this part. Right? So it's like this and then like this. So what is it going to look like? Like this? So it's going to be most likely just like this. So it's going to be like this and this part. All right, so it kind of looks like the flip of what we just did, but it's going to be something like this. You don't know. You don't know. This is just, well, could it be? No, it can't be right next to it because it's supposed to be slope. Okay, this is what's happening. The slopes, as you look at it, it's 0 and then more positive, infinity, right, on the right side. On the left side, sorry. And then when it comes and jumps over here, what's your slope? Negative infinity. So it jumps way down here. It does have to come down here. It can't be connected. Right? The slope on this side is not positive infinity. It's negative infinity. Very, very negative. So it's supposed to come down here. Right? So when you're looking at the slope, it's like this, positive, and then it's supposed to go, I'm sorry, not it's positive infinity, sorry. It's, the slope is positive infinity. And over here, the slope is also positive infinity. Right? Positive infinity, and then it goes to 0. It goes down to 0. Yeah, if you did that, though, it doesn't make sense. Okay, you mean like connect them? Yeah, you don't. Okay, so if you cross the x-axis, yeah, it doesn't matter if you cross the x-axis. Yes, you don't know. You don't know the location. It could be like, it's possible it would be above, like this. You could be like this. You don't know. It could be like that. Because all you know is it's like 0, and it goes to infinity, and then at 0, this is the only thing you know. And then it comes back over here, it's infinity again. You don't know actually the location up, or high or low. Right. Okay. Okay, another one. Let's say it's... Okay, what if it's like... what if we have something, actually another thing for this one, another possibility for this one, if you want to graph it as a continuous function, it's possible that this one could look like, another possibility, it could be like this, right? It could be this way too. It could be like vertical tangent. If you said it has to be a continuous function, it would be this way. All right, that's another possibility. No, I'm saying it could look like this, right? And it could also look like this. If it said that the f function is continuous, then this one doesn't count, right? This is not a continuous function for f. If they said the original function has to be graphed continuously, then this would be your solution. You see how, if you said, oh, connect these two together, you could connect them together like that. That's another possibility. You have 0, steeper, 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 infinity, and then, yeah, it's still infinity on the other side of this, right? And then 0.
Why would it be negative? Because it starts from, if you check the...
What's negative? Which part's negative? None of them are negative. This one.
Continuous. Yeah, this one, it goes into negative, right?
No, we're looking at the slope only. This is f. So the slope is almost 0, and then more positive infinity. That's 0, more and more positive, right? And then it's still infinity over here, right? And then it becomes less positive, 0 coming back down. So these two do match. Could be this kind of graph. Could be this kind of graph.
No, why couldn't for f we have it like one goes like the top like that, and then bring the second part to the positive axis? Like that?
Yeah, it's fine too. Yeah, it doesn't matter. Doesn't matter where this is located. So when you sketch it, you don't know. They'll tell you if f is continuous. They'll tell you want to graph the possibility that f is continuous, but you don't know the location on of the y values. You only know the shape of the graph and the x locations. Like you know that there's something happening at x equals 0. You don't know how high or how low to sketch these. These are all possible. You can sketch it all over here. Those all count. Yeah. Then this is a vertical tangent.
For
Yeah.
the right graph over there,
Mm-hmm.
can you draw the top like that and then just bring what you have up to the top but not connect it?
But not connect it. It's going to be a function though. Whatever you're telling me to sketch.
I mean, the last one that we drew was not a function either.
This is a function. This is a function.
The one that we drew here, that looked like this. It looked like
That's a function.
that's a function.
That's a function. Yeah, it passes a vertical line test. Yeah. This passes a vertical line test. There are no two x values this time.
That's not test vertical line test if we do, like,
That's a function also. I'm just not a continuous function. Which one? It's not. Okay, this is not a one-to-one function, right? Because it doesn't pass the horizontal line test. That's a function.
that still passes function test if you move this.
This is a function. Oh, you mean move this to the. Which part are you talking about?
Okay, so do you see the second part?
Yes.
At the bottom there?
Yes.
Just move that up. Don't
Yeah.
connect it.
But it's okay. Okay, so you want to make it not. Okay, so you're saying you just want to move this one here.
Yeah.
Something very bizarre. Could we do that? I guess you could do that. Nothing can stop you from doing that. I don't think you can. Let me think. If you have that, you could say, yeah, and just have like some sort of vertical asymptote here. It could be like that, infinity. Yeah, you could. Nothing stopping you from doing that. Yeah.
And then on the f prime graph, there's
Yeah.
a tangent at 0,
Yeah.
which means that the slope is undefined.
Yes.
Which means in a regular f function.
So it's very steep. Yeah, vertical tangent. I'm trying to draw it as vertical tangent. Vertical tangent at 0. So when you're sketching it, whatever you do, you just need to show some sort of like it needs to be very steep here so that it's shown as a vertical tangent there. Wherever, it doesn't matter where along the y-axis you show. Okay.
Because
It's a undefined slope. The f prime is undefined.
choose to make an asymptote or a vertical tangent.
Yes. Yes. That's right. Okay, so let's say it's like this. Let's do another one. Let's say it's like this. This. This is the f prime. I know it's easier to go from f. I think you guys can all go from f to f prime. That's much easier. But so I know I have a vertical tangent here at 0. This one another, right? Vertical tangent is 0. So what do you think? So if you're trying to make this a continuous function, then you can make a vertical tangent of some sort, and you can see the slope is what? Negative, some negative value, and then more and more negative, right? Or if you want to look at it as below the x-axis, just keep this up. Okay, so I can see that it's below the x-axis, so it's decreasing, and f prime's decreasing, so it should be a decreasing concave down graph. So it should be something like this. And then on the other side, I can see it's above the x-axis, so it's increasing. And it is a decreasing graph, so it should be concave down. So it should be concave down, decreasing, on concave down, increasing. So it should be something like this. Yeah, it's decreasing, concave down. Yeah.
No, it's increasing because it's positive.
This one. This one. Okay, above the x-axis. So it's going to be an increasing and then heading down, so concave down. Okay, so it should be this connected to this. So then your possibility is going to be like this.
Can it stay above the y-axis?
Yeah, it could be anywhere, anywhere. So it could be there. You just don't.
Does it have to be connected? Is that
If I say it has to be continuous function, it doesn't have to be. It could be also, it could be like this. Another possibility. If it doesn't state that f has to be a continuous function, then you could definitely sketch it like this. Right? And of course, you could shift this up or down, right? So our slope is almost 0, but negative, like some negative slope, right? Then more and more negative, negative infinity, and then it jumps to positive slope, very positive, and then back to 0. So it could be like this, like that. Those are all okay. Okay, next one over here. This one, you can tell you're going to do, yeah, it's a positive. Okay, so below the x-axis, decreasing and concave down, and this is decreasing, and then the concavity, it's heading up, so concave up. So decreasing concave down here, decreasing concave up here. So it's like this, and then this. Okay, so it should be something like this, right? It has to be a vertical tangent there. Doesn't matter where you graph in this position, right? So you can also say, okay, 0, I could see it's negative slope, more and more negative slope, and on the other side, very negative slope, back to 0. Does that make sense? Okay. Let's see. Let's graph a couple. Let's do a few more types of ln. Do an ln type. How do you sketch x times ln x? We did an e, right? Let me see. What did I do? Yeah, we did an e type. Let's do an x times ln x type. Okay. So first derivative. Do the first one. Keep the second one. Keep the first one. Do the second one. And then I have this ln plus 1, right? Okay, so I'm looking for when this is 0. What makes this 0? Is it possible? So if I do ln of x plus 1 equals 0, ln of x equals negative 1. But ln of x can never be negative 1, right? Because ln functions are, actually it could be negative 1, so e to the negative 1. So e to the negative 1, so I get x equals to e 0, okay, here. That's one of our zeros. And when you're sketching this one, we have a domain restriction. What is it? Before you even start doing it, this can't be negative. So isn't the domain this? The value here? Because ln is a graph like this, going through 1, 0 to the right. It's always got to be greater than 0, no matter what you do. So we know that our domain is x greater than 0. You got to cut it off. Okay, so when we're doing the f prime, and you're showing it, you have e to the 1 over e, right? 1 over 2.718 or whatever, this number. There's going to be a 0. If you're only showing that 1, you're going to make a mistake because I have only this 1, 0 for the prime. So the leading coefficient, you have to actually check here. If you check in here, you end up with, we can't actually sub this one because it's not a polynomial. You're going to have to check the points. So I have to cut this off at 0. There's nothing down here, right? The domain is 0 and up. Okay, so then first one, when you check this one, what do you get when you sub in something bigger than? So let's say e squared. So that makes this 2. 2 plus 1 is positive, so that's okay. Then if you check something less than 1 over e, so what's something less than 1 over e? It's like 1 over e squared, right? That could be less than 1 over e, isn't it? Right? So 1 over, yeah, this is negative 2. So negative 2 plus 1, well, that's negative, so we know it's negative here. Okay, so now we have those two. And then that means my original graph, f, has to be heading down, then up. So then this is a min. We have a minimum location at 1 over e. Okay, then do the second derivative. Uh-huh.
Be left of 0.
Nope, because it's not part of the domain. Right? We're restricted to greater than 0, so you don't have to look at anything less than 0. Okay, then the next one, because we're not graphing for this graph, there's nothing less than 0. So then the second derivative, so we're starting here. Take the derivative of that, 1 over x. The 1 goes away. So when is this 0?
Wait, how did you know that the right of 1 over e is positive?
Sub the point. I just subbed it in. 1 over e. So for example, we'll sub in like e squared, something bigger than 1 over e. Yeah, I sub in something nice. That's going to give you a nice number. Because it's, right, this is obviously 2.
Mm-hmm.
Zero to this one, f prime. We're checking what f prime is at that location. So if I have 1 over x, and then the 1's gone, 1 over x is there, then nothing makes this 0, right? So is second derivative ever 0? No, nothing makes a 0, right? Nothing makes that 0. So we don't have a, so for this one, when you're thinking about second derivative, you're going to get, technically this is, right, a hollow point, because you can't have that be 0. And then it's plus here and minus here, right? If you sub in points, these points make it positive, those points make it negative, which means the original graph is concave down and then concave up. Okay, but there's nothing actually here. Again, we can't go below 0, so it's all concave up, basically, right? To the right of 0, all concave up. Okay, try to sketch it. So if you try to sketch this one, what does it look like? So I have something 0. Okay, something's going on here. So concavity, we can't say. That's not a point of inflection. There's nothing on this side. And it is at 0. What is the answer? Could I substitute at 0? This is very tricky. Be careful. Could we substitute at 0? No. The value can't be 0, and it can never reach 0, right? It has to get close to 0. The domain's greater than 0. So technically at 0, it's approaches 0, but doesn't touch it, right? Yeah. It's not 0. You can't sub 0. ln of 0 is undefined. ln is a graph like this, right? You can't actually touch 0. No, because the domain isn't the domain doesn't exist here, so you can't actually substitute 0 here. It's undefined, right? You can't do ln of 0. It's just not possible. So what's going to happen is you're going to have it approach 0 is what's going to happen, right? We sub the 0 here. You see that 0 times something, right? So it's going to approach 0 when you sub in the point. And then check your lowest location. The minimum's at 1 over e. So I have a relative minimum at 1 over e. Substitute that to the original. That's 1 over e, ln of e. ln of e is 1, so it's 1 over e. So that location, 1 over e, wherever that is. Okay, so if I have 1 over e, 1 over e, let's say you don't have a calculator. Is it positive or negative? If I sub it in, it's 1 over e. It should be positive, right? This is 1 over e. Why am I writing negative here?
Because it's e to the negative 1, so it's negative 1 over e.
It's e to the negative.
Plug it into ln x, you get negative 1.
1 over e. Okay, so if I sub this 1 over e as a minimum here, I wrote 1 over e times, there's a 1 over e here. This is 1 over e. I wrote, there, I wrote e. This is negative. It's negative 1 over e. So it should be here. Yeah, so 1 over e, negative 1 over e. Okay, so I have that, and then what happens on the other side? And then we know it's like this kind of graph. So it should be doing this. Does it go to infinity on the other side? So as the numbers get larger, it does. It's getting bigger and bigger, and these are getting bigger also. So that's it. Then your sketch should be something like this. Yeah, that's it.
So how do you know when it crosses the x-axis?
X-intercepts. Let me see. Did I actually get my other x-intercept? I have 2 x-intercepts. What are my x-intercepts here? What makes this 0? I guess we should have gotten an x-intercept here.
0.
Right, so then we have, right, x times, you can actually go for the x-intercept. So 0 is one of them.
No, 0 can't be one of those.
Oh, not 0, hollow. So close to 0. And then the other one, this is possible because it's e to the 0. The other one's located at 1. Right? Yeah. X-intercepts. So I have an x-intercept at 1. You can always check for what your x-intercepts are and if any y-intercepts. Yeah. There are no y-intercepts because we said this can't be 0. So it's just a graph like this. Okay? All right. Okay, done with that. ln of, okay, how about this? ln of x over x. So I have what? F prime. So what can we say about the original? Like before you start, I guess, you can always try to figure out what the graph looks like based on your prior knowledge. You can tell there's definitely a vertical asymptote at 0, right? You can also see that there is an x-intercept. What makes the numerator 0? Well, it's when e to the 0 is 1, right? So I can see I have an x-intercept at 1. I've got a vertical asymptote at 0. The rest we're going to have to just figure out. What happens to the horizontal asymptote, if any? How do you figure out something's horizontal asymptote? You take the limit to infinity, right? So you can say, what does this look like? You might have to use the L'Hopital, right? Depending. So you have this one. When you sub in infinity, infinity, you can see both of them are going to infinity. So we might have to take the derivative. So if you do that, what do you get? Yeah, so you get 1 over x. Bottom is a 1, so it's just 1 over x. So 1 over x, we know what happens to that when you go to infinity, 0, right? So horizontal asymptote ends up being 0. So those are all things you can tell about the graph to start with. Any domain restrictions? Right, you got to look at the ln. So x is greater than 0. X greater than 0, horizontal asymptote, we have all those things. Okay, good. Then go ahead and try to take the derivative and see what we can find. So we have f. Yes. You know, what happens to the graph, right? When you look at horizontal asymptotes like this, it's what happens to the graph as you go to infinity or negative infinity. That's the horizontal asymptote. What is the value you approach? Okay, so here, f prime, first derivative. What do you want to do for first derivative? Quotient rule? You could do quotient rule. So you have denominator squared, low, bottom, derivative of the top, 1 over x, minus high, top, keep it, derivative of the bottom. So I end up with 1 minus ln of x over x squared. Okay, what can I show for this at the top? Okay, on the bottom I've had undefined for 0. On the top I have ln of x is 1, e, yep. So I have that as an x-intercept. E is an x-intercept, 0, hollow. That's the second double root, so circle that. You're not going to change signs around that. The square. Okay, so what do we have here when we substitute? The first derivative, okay, the leading coefficient looks negative. Yeah, but we're not sure. Go ahead and substitute, because I said for ln ones, you should check. Yeah, so then here, if I said like e squared, something like that, you could see it's negative, right? It's 1 minus 2. So yeah, so then we'll get negative here. So this should be plus plus, most likely. And then you can check. Between 0 and e, what can you check? 1. Yeah, 1 is the number between 0 and e. So e to the 0 makes this is 0, right? That's 1. This is positive. And that's okay. It's positive. And it should stay positive again, even on the negative side. So negative 1. Actually, you can't check that. Why no negatives? I have to restrict my domain. I didn't do that. So there's nothing here. You don't have to check anything after 0. There is nothing that exists there, right? Okay, so that means this is f prime. So what does my f graph look like? It's increasing, then decreasing. So it means I max out at e. So that means I have a relative max. Let me look. Isn't this like this is the whole thing? Yeah, you're doing it the whole time, I think. For 5.1, increasing, decreasing, concavities. Relative maximums and relative extrema for polynomials is 5.2. 5.3 is with vertical tangents. 5.3 you have vertical tangent. Let me see. 5.3 has rational functions. Okay, so what we're doing right now. And then 5.4, absolute, we have to do that, yeah. And sine and cosine, yeah. Some with sine and cosine in it. And ln. Okay. Okay, so we have relative maximum located at e sub in e, so it's ln of e over e. That's 1 over e, right? So e the relative maximum. Okay. Next one, second derivative. Okay, so second derivative, this one, what do we have? 1 minus, we do it one more time, right? We have to do another quotient rule. So we have x to the 4th, low derivative of the top, so 1 goes away. This guy, minus 1 over x, minus high, 1 minus ln of x, d low, so it's 2x. Simplify, so I have negative x plus, minus 2x plus 2x ln of x over x to the 4th. Is that right up to there? Yeah, so this is negative 3x together. I'm going to simplify this right here. Did I make a mistake? I think that's right, right? Negative 3x. Did I do that? You can factor it out and cancel, yes. So I end up with that. I end up with negative 3 plus 2 ln of x over x to the 3rd. And then second, right, so ln, you could do second degree. This guy becomes 2 ln of x equals 3. So ln of x equals 3 halves. So it's e to the 3 halves. That's one of the zeros. So 0. And then e to the 3 halves. And that's solid, right? Because it can equal to that. And then sub in something. It should be positive when you sub. So if you sub in something like negative 3 plus 2 ln of e to the, it's bigger than 3 halves. So 2, right? So that makes this 2 times 2. So negative 3 plus 4, positive. So it should be positive, and it should be minus here, and then we don't care about this part. So you can check the next one. Between 0 and that, so such as 1, right? So it's negative, yeah. It's negative 3, and this is 0, right? E to the 0 is 1. So it's negative 3 is negative. So it's like this, plus minus. Okay, so I've got those two, and then that means the original function is concave down and concave up. So that's an inflection point. E to the, so I have an inflection point at e to the 3 halves. Sub in e to the 3 halves to the original function, so that's 3 halves over e to the 3 halves. Right? Everything good up to here? Yeah. Okay, then let's try to graph it. Okay, I'll let you attempt to graph it. Give you a second to do it. So if you're not allowed a calculator, that means you do relative positions. Let's say you have no calculator. So you just know that this is bigger than that, for example, right? 1 over e is 1 over 2 point something. This is smaller than that then.
Like ln x plus, like ln whatever, like it's on the packet. Or like root 2, right? Like the packet that I gave you.
Uh-huh.
The ones that we can work on in class. They're so hard. Actually, they're not that bad. Really? I got up to 4. I just didn't know what to do. Well, yeah. After, like, I think the first one was pretty bad. But there was like e to the everything.
Mm-hmm.
And Arizona was like, there's a bunch of e's. And then she was like, oh, you can just tell. I know. Okay, like,
Without a calculator.
Number 2.
Okay.
Number 2, that's just like, oh yeah. No, wait, no, number 2 is what I was oh, like 1 over e plus 1 minus 1. Yeah. Okay, yeah. So what's number 1? Number 1, they're just like ln 1 plus 1. You should obviously know that that's less than 1 over e plus 1.
Oh.
How are we like, oh, great, yeah, of course.
ln of 1 plus 1? Well, ln of 1 is 0.
E minus 1.
E minus 1, yeah?
And then 1 plus 1 over e plus 1.
1 over e plus 1.
And then ln 1 plus 1.
ln of 1 plus 1. Okay, let's figure that. This is 2.717, so that's a 2 point something minus, so 1.7 something. This is 1 over 2.7 something, so it's like,
1.5.
yeah, this 717. So it's like this. So this is less than a half. So it's a 1 point, yeah, something small. Well, less than 1, like definitely at most this big. This one, ln of 1, 0. So that's just 1. So you can compare them. That's true. It's this, then this, then this. You could.
You didn't know the number E.
Oh, you have to know it.
Yeah, I don't know it.
Well, now you know. 2.7.
I might just learn it right now.
You have to know it. E is 2.7.
2.8.
You can, yeah, approximate 2.7. 718, I think it's 2.718, right? Did you do it?
Yeah, 2.7.
Yeah, but approximately 2.7 is good enough. 2.7 is good enough. Okay, did you guys figure something out? So we have a maximum at E, 1 over E. So that's 2.7. And then this is 1 over 2.7, roughly. Okay, so then that's like E, 1 over E. And then we have inflection point here. So inflection point's to the right of this, right? E to the 3/2. So that must be bigger than E. So it's over here. And then is it lower or higher than this point? And we know we have a horizontal asymptote of 0, so it kind of gives it away. It should, that's the max. It has to come back down to this horizontal asymptote, right? We said the horizontal's here. So it means then it must be dipping down here. So it means this is E to the, wherever this is, E to the 3/2. And this one is 3/2 of that. So we don't know where it is. I think approximately just somewhere less than that, right? It's 1.5 times, 1 over E to the 3/2. So definitely less than this, right? Because E to the 3/2 is a bigger number than E. So 1 over, right? 1 over E to the 3/2 must be less than 1 over E, right? And then we're multiplying that by 3/2, 1.5. But anyway, it's somewhere over here. So we know it's going to come down like this. And then what about the 0 location? At 0 doesn't exist, right? What about the prime? Original graph, 0. No, right? It's only going to approach the 0. What happens when you get like close to this? Any other x-intercepts? Right, 1. So ln of, we already wrote it, x-intercepts 1 here. So I have something here. It's going to actually cross through the x-axis. And then after that, as it gets, it's going to approach what? Vertical asymptote is 0. We have a vertical asymptote. So it goes to negative infinity. If you substitute like 1 over 100, okay, as you get close to 0, we know the answer for ln. What is that? Like, it's negative infinity. So negative infinity over 1 over 100 becomes, it's still negative infinity. It doesn't matter, right? So it's just going to head down. So it's going to be concave up, as we showed in this graph, up here, and then a concave down, the rest. Concave up, and then concave down. And then over here, relative max. You can always pass horizontal asymptotes, never verticals. Yes.
Isn't the dot right?
Vertical asymptote you can't go. 1, this one, E 1 over E. Yes, that's, I was trying to go to the max, yes. Not the best graph, okay, like that, okay. That's trying to be the max, okay. E 1 over E is the max. And it comes back for horizontal asymptote. So basically a lot of the ln x, E graphs, they often have horizontal asymptote, right? And vertical, you can probably figure it out, a lot of them, okay? So you're going to do them for homework, so pay attention to how they look when you do them for homework. Okay, other than that, let me see. Okay, let's do some with absolute value. Here's a conceptual question. If f is continuous on an interval from a to b, and you have at x equals to c, let's say we have a relative maximum. Let's say this exists. Okay, so what things can you say are true? 1, is the prime at c, does that exist? Does the prime, let's see, what else? Second derivative exist? Does f, what's true? I guess I'm asking, what things could you say is true about this? Like 1, 2, or let me see what other choices here. F prime exists. F. Okay, so which ones are? Oh, I did? Okay, they called. Okay, so here what do we have? F prime, F double prime, and the original. Right, the third one's true, because if you have a relative maximum at C, first one exists. How about the first one, number one? Not necessarily. How come? Because relative max could look like that, right? It could be continuous. We already said that you could have a derivative at C that's, right, dne. Right, because the first derivative doesn't exist, the second derivative doesn't have to exist either. So the only thing that you know is for this. Because you have to take the prime of the prime, right? If your first derivative is already dne, how do you take the derivative of that dne? You can't, right? Okay. Yes, because we have a relative max. It has to be on the graph. That has to happen. Okay, let's do one that's a absolute value case. Okay. Then you have to break it up. Okay, so if it's like y equals to 1 plus absolute value, 9 minus x squared, and it's negative 5 to 1. It exists over negative x homework. Okay, then you have to have a, let's find the relative extrema, meaning find the relative max and min. And then we want to compare with the endpoints. You want to compare with the endpoints to get the absolute. Okay, so anyway, relative extreme and absolute, both. Find the relative extremes and absolute extremes. So first thing, write it into a piecewise function. Write this as a piecewise, figure out the different points that you need to break it up. So where are we going to break it up? 3 and negative 3, right? We're going to set this thing equal to 0. So we can see if we set 9 minus x squared equals 0, obviously x is positive negative 3. So when you break this up, you have 3 and negative 3 to worry about. When does it stay positive for this guy? The outside, well, look at the leading coefficient. Yeah, look at the leading coefficient. The inside's, it's negative, positive, negative is what you expect. So it's going to be like this, right? Leading coefficient negative. So it means you need to keep it here and then change it for those two, right? So here then you want to do change. So if you change, it's 1 minus 9 minus x squared. Keep in the middle, it's 1 plus 9 minus x squared. Simplify, that's 10 minus x squared. The two negative regions out here, it's negative 8 plus x squared like this. Yeah, and then from here, those two, let's write that out. So you have two things here. We've got a 10 minus x squared. We've got negative x squared minus 8. So that's for the two. What was that? The negative regions, we have to change the sign, right? The positive we keep. So we know definitely for the outside, negative. So we know that this one is for when x is greater than 3 or when x is less than or equal to. That's a negative 3. It doesn't matter which one you set to be equal. It's going to be continuous. So that's fine. And then this is the in-between one. You could decide whether to put the equal to on the top one or the equal to on the bottom one. But if you check at 3, you get 1. You check at 3 over here, you get 1. It's continuous. You know it's going to be a continuous. It's basically a parabola, and then you flip it up, right, with its absolute value part, right? You know that, like, what is this graph before you even begin? Right, it's a parabola. It's like x squared. It's like this graph, which is facing down, starting up at 9 like this, and then you are flipping up the like that, and after that you shift it up 1 unit, so your overall graph is going to be like that. So you see those are going to be our relative minimums and also our absolute minimums. It's a sharp turn for sure because it's a parabola, right? You flip it up, so you know that there's going to be dne for slope over here. Okay, so once we have this one, take what else? Okay, also, before you do anything, I said that I want to only do these. I'm actually not going across the whole domain. So we're only going from negative 5 to 1. So if that's the case, then what do we need to do here? So between negative 3 and 3, where do we need to stop? 1. And over here, I can't go up to 3. Yes, because they told you to only check between negative 5 and 1. So here, I can't go greater than 3, can I? Yeah, so that's out. this one for x is less than -3, what do I do? I have to keep this as x is less than -3, but then you have to restrict it to be greater than or equal to -5. Does that make sense? Okay, so you're only checking between -5 and 1. Okay, so now that I have those, okay, now take the prime. Go ahead and do it. Take the prime. Oh, they said I left it there? Okay, so then we have the first derivative. What do you do?
-2x.
-2x and 2x. And what about, okay, so this is from, so 1. Yeah, -5 to -3. Okay, so hold on a second. We have, and then we have to check at negative, okay, so at -3, that's fine. The first derivative, okay, -3. So we have, okay, so then we have -5 to -3, okay. Okay, so if you check at -3, what happens? If you, do the what?
They're both 0 at 0. So there's -2 at 0.
No, I'm checking -3. I wanted to check to see if it's differentiable at -3. Right, this is the part that's going to have a problem, the border points. So if you sub -3, that gives you 6. Sub a -3 here, it gives you -6. So that's a problem at -3. So we have to write x equals -3. So that means that you only can approach it from the right, or so don't make this equal to. Yeah. So basically from one side it's negative, from the other side it's negative. So actually at -3 we have to say d and e. Okay, so those two. So it's not differentiable at -3 is basically your conclusion. Okay, what else? If you substitute, so go ahead and try to graph it. We have, if you take another derivative, you'll see that it's, yeah, it just goes to constants. Okay, so what is this going to look like? Right, so then this, you can tell for the first derivative, you get what? 0. 0, right? We care about 0? No. Let me see. Leading is negative, and I only care about from -3 to 1. Okay, so then negative, positive. Okay, so this is for the prime. So that means the original function is, so should have a max at 0. That's what it tells us. Okay, the second part over here, between -5 to -3. Yeah, I was thinking about these things here. Okay, -5 to negative. You don't have to. You can do it on the same graph. So to -3, there are, it doesn't even get to 0. Right. So then in that case, this other part is always going to be what sign? So yeah, always going to be negative when you sub it in. So on the other side, so if you graph this a bit longer, anyway, over here it's always negative. So we end up with a, if you want to graph it together. So it's like -3 to -5 inclusive. Okay, so that was negative, positive, and negative, yeah. And this is at 1. Hollow here. So it'll be like this. It'll be negative and then positive and then negative over here. You sub in negative, you get a negative. Okay. So then we have a negative, positive, negative. So probably relative minimum at -3, relative maximum at 0. Okay, so -3, 0. So sub in -3 into the graph. What do you have? 1 plus -3 gets us, you already know what the graph looks like, so you can cheat with this one. You already know, right? You don't have to do the piecewise actually to do the whole thing. We already knew it was like this, and it just shifted up 1, right? So if you sub -3, you have 1 plus 9 minus 9, so 0, 1, right? So -3, 1, which is what we expected here. So, okay, based on the knowledge we have, it's that shifted up to 1. This is the graph. We know that already. So then I have a maximum at 0. 0 is 10. And then it's going to come back down again over here, but it's only going to make it to 1. We only want to go to 1. Check your endpoints. So endpoints are 1, sub 1, you get 1 plus 8, so 9. And the other endpoint was at -5, so sub -5. And that's 1 plus 9 minus 25, right? Did I square that? Okay. Is that right? 1, yeah. If I sub in the 1, I get 8 plus 1, yeah. So this one, when you sub in -5, I get 9 minus 25 is a -16, so positive 16, positive 17, right? So -5, positive 17. Okay, so I'm going to -5, positive 17. So we're way up here. And then over here, the other endpoint is 1, positive 9. No, 0, 0, 10, right? 1, 9. And then that's it. So I know it's going to be here, upside down parabola. Based on what we already know. Do not try to graph them purely based on the piecewise. Just sketch the function quickly. You already know what the graph looks like. Right? Just do this graph, which we know is a parabola facing down. You guys don't know how to graph it, right? Parabola facing down, cut it off, and then shift it up 1. That's it. Okay, so then we don't have the arrows, right? Because we have to do the endpoints here. So it should match up with all of these over here. So what's our relative minimum? This one. Relative maximum would be this location. Absolute minimum at x equals -3, right? Absolute maximum. Where's absolute max? X equals -5. Yeah, it's 17 at x equals -5. That's right. Right, you check your other locations there. Okay. Other than that, let me see if there's anything else I want to talk about. I think that's pretty much it. Stationary points. Stationary points. What else? This. Why is this not a stationary? No, this is not a stationary. It's D&E. Yes, it doesn't have a slope here, right? So only this one's a stationary point. Right? Okay. Let's see. Anything else? Okay, I think that's all we have time for. We're going to have to talk optimization next time. The word problems, we'll do it next time. Any other questions? Were you able to figure out, now do you think you can do your homework assignment?
No. All I did is after class